So last time we stopped at looking at Schrödinger's equation, and I noted that there's a lot of interpretation that needs to be done to even begin to understand the equation. But there's actually a little bit more to it. The formalism is complicated by the fact that measurement takes on a particular type of weird form, namely that the operators, which we'll kind of touch on, represent measurements, and the eigenvalues of those operators are the allowable possible values that the measurement will give. So one of the problems I have with quantum mechanics is that it seems to be very hard to break up into little pieces and explain each little piece bit by bit. So what I'm going to do is kind of show you an overview and kind of explain how the parts kind of work together, even though we don't really understand the parts quite yet. So what we have is a state vector, this psi and the Schrödinger's equation that I showed you before, showing the quantum state of the system. And that system evolves according to Schrödinger's equation, and that is the state evolves according to Schrödinger's equation. And what's involved here, again, are more operators, which we'll have to kind of understand what they are. And these operators end up also being used in measurements. And the measurements give you operator eigenvalues, which are the outcomes of the measurements. Now, of course, Schrödinger's equation only uses a few special operators: the Hamiltonian operator, the time derivative operator, multiplied by h bar. But there are lots of other operators that are of use. And really, the next section I've had to talk about has to kind of, expound on what vectors are and what operators are and what eigenvalues are. And hopefully at that point, we can really start talking about what quantum theory actually is.